Okay, now for this other form of a quadratic function, this one that's the textbook refers to as the general form. This is the form you're going to see a lot more often than that standard form from the previous example. So the only problem is, in this general form, you can't tell exactly what your shifting value is or what your reflection or anything like that. You can't use the transformations because of the way this is written. So there's some extra things you got to do to kind of prep it to find the vertex. I need to show you a very, 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 very important calculation that you do need to commit to memory. For quadratic functions, if you don't have that standard form that tells you the shifting and the vertex, it has this form, the first thing you need to do is perform this calculation right here. X equals opposite b divided by 2 times a. And remember, the values of a, b, and c are the same thing as from the quadratic formula. The a is the value in front of your x squared. In this case, a equals 2. B is the value in front of your x. B is negative 4. And c is the constant term, the plus 4 right there. So the a and the b that are mentioned right here come from those values. So when you do that calculation, that just tells you the x coordinate of your vertex. But remember, you got 2 coordinates you got to plot. You need the x and you need the y. But since you have the function here, whatever your x coordinate is, you just plug it into the function to get the y coordinate that pairs with it. And that's the way you have to get your vertex from this general form of a quadratic function. So let me show you that calculation first. Alright? So we've got a equals 2, b equals negative 4, c equals positive 4. You don't need c in this calculation, but, just reminding you what a, b, and c stand for. So to determine the vertex requires 2 calculations. First, x equals opposite b divided by 2 times a. So when I plug in my numbers here, the opposite of b is positive 4 divided by 2 times a, which is 2 times 2, another positive 4. You get x equals 1. And keep in mind, vertex is 2-dimensional. You need an x and a y coordinate to plot it correctly on your graph paper. So now you go to the function formula and you just plug in x equals 1, and that gives you the y coordinate. So the y coordinate is f of 1. Just plugging that in. And the calculation there would be 2 times 1 squared minus 4 times 1 plus 4. And follow your order of operations carefully. That's going to be 2 minus 4 plus 4. So should end up giving you positive 2 as your y coordinate of the vertex. So with those both together, your vertex is located at x equals 1, y equals 2. Alright, so let's go on and plot that. Positive 1, positive 2, there we go. Okay. Now, if you want, part B is actually optional, but part B is kind of handy if you want to rewrite it in standard form so that way you can see exactly what the transformations look like in order to graph it. You've got the vertex plotted. You know the value of A, so since the value of A that's used in the general form is going to be the same value of A used in the standard form, what this means is the standard form for this function would be f of x equals 2, and again, that's my A value right there. Open parentheses. The vertex got shifted 1 click to the right, so that means in the parentheses here, I would need to indicate a rightward shift of 1. So that would be x minus 1 quantity squared. The vertex also got shifted up by 2, so I need to indicate a vertical shift of 2. So plus 2 would tell me that would make the vertex stop right there at that point. Okay? So that way, if you need it in this form, it might come in handy for plotting purposes on the graph paper or anything like that. So since I've got my vertex shifted, I've also got a stretch factor of 2 for this one. So if I go 1 click to the right, I usually go 1 click up. But again, that means to double your y value. So double your y value. 2 clicks to the right would go 4 clicks up usually, but I need to double that to 8. So I'm actually going off my grid right there a little bit, but that's roughly where it would fall. And then you can use the symmetry line for the parabola to plot points over here on the left side of the vertex. Okay, so this one would look something like this when you finally get it plotted. Okay, roughly like that. Okay, so we got the graph sketched, and I really gave myself way too much room there for that, but now going down here for the intercepts. Hopefully you can tell from the graph, you have no x-intercepts. The vertex is up above the x-axis and it opens upward from there. So, according to the graph, the answer here should be none. But again, let me show you the algebra behind that. And to show you the alternative, if you didn't have it in this form and you had to rely on the original general form up there, you set it equal to 0 for y, still, because you're finding x-intercepts. And based on this is now a quadratic equation that you can either factor or use the quadratic formula on. I don't think I can factor that one. I can pull a 2 out, but what's left over is going to be x squared minus 2x plus 2. And if I try to factor this trinomial that's left over, I can't come up with two numbers that multiply to positive 2 and also add up to negative 2. So I need to approach this with a quadratic formula. So if I take the quadratic formula to this, to solve it, I'm going to get x equals opposite of b. And again, don't let the 2 that you factored out mess with you. The values that are inside the parentheses there are all you need to apply the quadratic formula to. So x equals the opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. Okay? And keep in mind, we should get an answer that tells us no x-intercepts. If you simplify that discriminant, the number underneath your radical, you're actually taking 4 minus 8. You're taking the square root of negative 4. So, since this is actually trying to make you take the square root of something negative, see, this will lead to two complex solutions, which on graph paper, you're only graphing real numbers. So since we can't actually graph complex numbers, that physically means that there are no x-intercepts on the graph. Okay. Or if you just want to say none, there are none x-intercepts, what are the x-intercepts? None, that's fine. Okay. Y-intercepts, again, we can determine the y-intercept by looking at the graph. Apparently it occurs on the 4 hash mark of the y-axis. But let me remind you again, to find y-intercepts in general, you plug in x equals 0. You see, the way things swap up, x-intercepts, let y go to 0, solve for x. Y-intercepts, plug in x equals 0, and then just evaluate the function. So all I need to do there is evaluate f of 0. Which is going to be 2 times 0 squared minus 4 times 0 plus 4. And it gives me a 4. And that's consistent with the value that we got in the graph. It does cross the x-axis at the 4. So our y-intercept is definitely 0, 4. But of all the calculations I've shown you here, this calculation right here is very, very, very important. If you're given that general form for a quadratic function, you've got to use that x equals minus b divided by 2 times a to completely get the value of your x coordinate of the vertex. Plug it back into the function, and that tells you the y coordinate for the vertex. All right? So I'm done with this snippet of class. What I'm going to finish next are the application problems that you're using with these quadratic functions. So I'll be back here in a second.